Hello everyone, I'm Norman Wahlberger. We're talking about the mathematics of music. And today we're going to be talking about a more mathematical aspect of things having to do with scales and modes. So I want to take you aspiring and practicing musicians and bring you into the mathematics classroom just for a little while, okay? I promise it's not going to be too onerous, but you are going to be subjected to some sort of logical reasoning, and I'm going to try to make the case for this new terminology and notation that I'm going to introduce. But I hope that by the end of it, you'll see that there's a kind of a logic to this, that it sort of makes sense, and that it will simplify a lot of your understandings. Okay, so I'm going to be giving you some mathematical tools that will really help you potentially in thinking about music and the various possibilities for playing, for creating music, and for going beyond our familiar frameworks. So the start today is not on a piano, not on a guitar, okay? I want to think more conceptually in terms of this chromatic scale that we've talked about, this 12-tone chromatic scale, which is, at least after we've accepted the somewhat approximate nature of an even-tempered or well-tempered scale, it's quite a natural framework for things. So we've got these 12 tones, which we're calling M0, M1, M2, all the way up to M11. And we're going to refer to this as a clock scale. It's kind of an alternative to seeing a keyboard or seeing the fretboard of a guitar or something like this. Okay, so these various things are called tones, and there's really only 12 of them, and after that they kind of repeat, like C. You know, when you go up the C scale, then you eventually get to the octave, and then that's another C, and then it sort of repeats. Okay, and in this framework, the interval between successive notes, say if we're going this direction, that represents going up tonally or in frequency, that interval is called a one-step, and bigger intervals are correspondingly the obvious thing. So between here and here, that's a two-step, etc. Okay, so in this video, we want to get at things like scales, scale types, modes eventually, interval sequences, and there's going to be some cyclic symmetry around, and maybe not in this video, but we want to move towards reverse symmetry in some future video. So I'm going to be looking at these things with a view of trying to be precise and to clarify what's going on and to choose some good notation and terminology that will help us. So to help us apply some mathematical thinking to this situation, I'm going to shift our notation just a little bit if the context is clear. So instead of calling the notes M0, M1, etc., we're just going to refer to them with the numbers. 0, 1, 2, 3, up to 11. Okay, so MI is going to be replaced with I. So there's a possibility of confusion here because the numbers, after all, are used for all kinds of things. And in particular, the numbers are also going to be used when we discuss intervals, which is really about the relationship between two notes. So we may have to think about notation that makes it easier to distinguish those different usages. But anyway, so that's a good starting point. So now we can just refer to these tones with these numbers, 0 to 11. So for example, let's sing a song, Mary Had a Little Lamb. And we're in this key that is labeled 0. Now maybe this is middle C, but maybe it's not. Maybe it's A, maybe it's E, whatever it is. Okay, the actual absolute position of these tones is not really that crucial here. All what we're really talking about is the relative position once we have sort of fixed a melodic structure. Okay, so 4, 2, 0. 4, 2, 0, 2, 4, 4, 4, 2, 2, 2, 4, 7, 7, 4, 2, 0, 2, 4, 4, 4, 4, 2, 2, 4, 2, 0. There, it's a little song, okay? So maybe to organize this, we could, there's a kind of natural time signature. We could make bars, okay, sort of representing units of the song, okay? And, I suppose we could even indicate where the beat goes, like 4, 2, 0, 2. So if I'm sort of tapping my foot, 4, 2, 0, 2, 4, 4, 4, 2, 2, 2, 4, 7, 7. 4 2 0 2 4 4 4 4 2 2 4 2 0 0. Okay, something like that. Now, I'm not proposing this seriously, but I'm just letting you know that there is some possibility of actually writing down some music in this kind of framework. We're not absolutely tied to the usual bars and round little notes with things. Okay, so just a thought. But what I want to represent here is that here we have the scale, and we're not necessarily really assuming a major scale here because we have all 12 notes here in this chromatic story. Okay, we do not have yet a distinguished scale really. Although in this particular song, I'm sort of choosing the scale, the major scale, which is built on this this tonic called 0. Okay, so let's turn to the issue of scales. The first natural question is, what is a scale precisely, or at least reasonably precisely? Well, there's a range of different approaches we could take. I'm going to try to take a relatively simple one based on our clock scale. And I'm going to say that a scale is an ascending is going up, so that's corresponding to a clockwise going in this direction around the circle. It's an ascending or clockwise sequence of tones, okay, starting and ending on the same tone and going around exactly once. So we start somewhere and then we go around, we choose a sequence in this direction until we get back to where we started, and we've gone around exactly once. And that's what we're going to call a scale. So for example, here is a scale, and I'm going to indicate that scale on our clock. Okay, so the scale starts with 2. So let's circle that. And that's a special note, so I'm going to actually put a little like a support there, okay? That's letting us know that that note is special because it's the starting note. It's also the final note, okay? So we're at 2, and now we've got to go in this direction. So the next one is 4. The next one is 6. The next one is 7. Okay, we're going in the right direction. 9. Okay, I couldn't put 8 next. We have to keep going in this direction. 11. Okay, and then we're still going in this direction. 1. Okay, and then we end up with 2. We end up where we're starting. Now notice that this sequence of tones that begins and ends with 2 is enclosed in pointy brackets. So that's just an arbitrary convention that I'm making here. Now, I don't know, what kind of terminology exactly is out there in the musical world. I mean, I've been playing instruments for decades, etc., but I haven't really seen any, consistent notation in this direction. So I think I'm pretty safe in being allowed to make this convention. All right. So let's do that. Let's say a scale then is signified or specified by these pointy brackets. When we see something in a pointy bracket, a sequence of notes or tones, we know we're talking about a scale. Now there's a few additional definitions associated with the scale. The first is the tonic of the scale. That happens to be 2. So that's this unique point where we're starting and ending. So we're going to call that the tonic of the scale. Okay, the scale's name is S, the tonic of S is 2. And another thing that we're talking about is the size of S. Okay, now this is some kind of list or sequence. It has 1, 2, 3, 4, 5, 6, 7, 8 elements. But this last one is really the same as the one we started with. So there's really 7 distinct, 1, 2, 3, 4, 5, 6, 7 distinct elements in this scale. So that's what we're going to say is the size of S. So in terms of this picture, it's just the number of circles. The circle does not get counted twice, just gets counted once. So 1, 2, 3, 4, 5, 6, 7 circles. The size of this scale is 7. So that's what a scale is. So now we're going to introduce the interval sequence of a scale. Okay, what is that? Well, it's also a sequence which is going to record the successive differences between elements of the scale. So it's going to record the differences. So, for example, if S happens to be 2, 4, 6, 7, 9, 11, 1, 2, then the interval sequence of S will be denoted by I of S. That's the following. And that's given by looking at the successive differences. So to go from 2 to 4, it's 2. To go from 4 to 6 is 2. To go from 6 to 7 is 1. To go from 7 to 9 is 2. 9 to 11 is 2. 11 to 1 is also 2, because that's 2 on the clock, okay, which is how many steps you have to take to go from the 11 position to the 1 position. You're going in the up direction, so you have to take 2 steps. And go from 1 to 2, that's 1 step. So the number of elements in this interval sequence is equal to the size of S. There are 1, 2, 3, 4, 5, 6, 7 elements in this interval sequence, which corresponds to the size of S. The size of S is 1, 2, 3, 4, 5, 6, 7. And notice our terminology that the interval sequence is going to be enclosed in square brackets. Mathematicians like to do this. We like to have terminology that allows us quickly to look at something and see what kind of an object it is. Okay, so that's a big help. We can look at this and say, that's an interval sequence because there's square brackets around it. We don't have to think too hard. This is a scale because it's got pointy brackets around it. We don't have to think too hard. Now, this is a very famous kind of interval sequence because it's exactly the interval sequence corresponding to a major scale. And this, in fact, is what we usually call a major scale. Now, if you've been trained in classical music theory, you will have seen this kind of thing before, but in the context of whole tones and half tones, which, honestly speaking, is quite unfortunate, okay? Because there's no need to introduce fractions into this story. The fundamental step is a 1 step, which is usually called a semitone, okay? Which is unfortunate, sort of unfortunate terminology. And it's terminology that really arises because the original major or minor scales are sort of thought of as, kind of the starting point. Even though the major scale doesn't consist just of whole tones, there's some half tones in the major scale too, but for some reason what we're calling the 2-step is denoted by a whole tone, and that's considered to be sort of more important. But in any case, we're sticking with an integral presentation of things, okay? And that's going to be really important for us and makes the mathematics so much easier, okay? We're going to stick with integers. And let's note also that the total number of elements, if we add up all of these elements, 2 plus 2 plus 1, that's 5, plus 2 plus 2 plus that's another 6, plus 1, that's a total of 12. It's always going to be 12, okay? The total number of elements in an interval sequence, if you add all of these elements up, you're going to get 12. And the reason is because you're starting and ending at the same point and you're going all the way around the circle. So the total number of steps that you're taking is 12 because that's how many steps there are going around the circle, okay? So that's an important thing to remember. Okay, here's another one. Here's another scale S. It's a scale 10, 0, 1, 3, 5, 6, 9, 10. It starts and ends at 10. We can see that it's going around, so we're starting at 10, sort of 10 o'clock, and then 0, that's like 12 o'clock, 1 o'clock, 3 o'clock, 5 o'clock, 6 o'clock, 9 o'clock, 10 o'clock. We're back to where we started. We've gone around once. Okay, so that's a legitimate scale. And the interval sequence for it is, okay, really the difference here, okay? So this is like 0, but it's effectively the same as 12. So there's a step of 2 to go from the 10 to the 0. So that first thing is 2. And then a step of 1, and then a step of 2, and then a step of 2, and then a step of 1, and then a step of 3, and then a step of 1. Okay, so this is hopefully easily recognized as a major scale. That's the integer sequence that characterizes a major scale. And this is an integer sequence that signifies one of the minor scales, melodic minor scale. So these are both sort of important sequences. And if we actually played on a piano or a guitar and play this sequence here, we sort of recognize that these scales are somewhat familiar. Okay, so there's the scale. There's the interval sequence for for the scale. Now we're able to say when two scales are of the same type, like they're both major scales, or they're both melodic minor scales, or they're both pentatonic scales, or something like that. Okay? So the definition is very simple. Scales S and T are of the same type precisely when their interval sequences are identical, when I of S equals I of T. So for example, here's a scale, S. Okay, it's 0, 3, 5, 6, 7, 10, 0. 0, starting there, 3, 5, 6, 7, 10, back to 0. Okay, that's a scale. The interval sequence for S is what? Well, that's a step of 3, and a step of 2, a step of 1, another step of 1, another step of 3, there's a second 3 step, and then a step of 2. And let's just check that the total is 12. It's like a little check, so that sum is 6, that sum is 6. So yes, indeed, it's 12. Okay, here's another scale, a scale called T. It starts over here with 7. It goes 7, 10, 0, 1, 2, 5, and back to 7. Its interval sequence is from 7 till 10 is 3, 10 to 0 is 2, then we add 1, then we add 1, then we add 3, then we add 2. Interval sequence for T is 3, 2, 1, 1, 3, 2, which is the same as the interval sequence for S. So these two scales are of the same type. Okay, so they are the same type. In fact, this is the type of a blues scale. Okay, it's very sort of standard scale in jazz and in blues. Okay, so if you heard these two scales played on a piano or a guitar or whatever, you'd instantly recognize that they're the same scales. It's just that one is a sort of a translate of the other. And what actually is the relation? Well, on the clock, what we've done is we've really just rotated things, haven't we? We've just really taken this pattern of green circles and we've rotated around. And you can think about that in two ways. You can think, well, what we've done is we've basically moved in the clockwise direction by an interval of step 7, okay, going from here to here. So we've rotated the whole thing by 7 steps to get this thing down here. So that this step going from here to here corresponds to this one going from here to here. So in music, like let's say we were organizing things so that this 0 corresponded to middle C on the piano, okay? Then note 7 would be a perfect fifth, or a step 7, which is nicer. That would be G, okay? So this would be a blues scale built on C. C, E flat, F, F sharp, G, B flat, D. This would be the corresponding blues scale on G, which would be G, B flat, D, G, B flat, C, sorry, D flat, D, F, G, okay. And they're separated by a fifth in terms of going from here to here, we're going up a fifth. Alternatively, okay, you could also think about going the opposite direction. You can think about, okay, one way of going from here to here, another way is to rotate in this direction by 1, 2, 3, 4, 5. The complement of 7 is like 5. So that's like a perfect fourth. Okay, that's another way of thinking about what we're doing, is we're taking the C scale and going down a perfect fourth to the G. Both of those are equally legitimate ways of thinking about the relationship between these two things. But in terms of actually the clock diagrams, the scales as these sets of notes on the diagram have just been physically rotated around. It's a physical rotation. This is why group theory becomes important, because group theory is all about things like rotations and more general transformations and how they combine. Now there's a simple but important observation to be made here. That a scale, say like this one here, this G blues scale, 7, 10, 0, 1, 2, 5, 7, that scale can also be specified by two pieces of data. Namely, knowing what the tonic is. The tonic is that first note, which is equal to the last note. So if we know the tonic of the scale, and we know the interval sequence of it, 3, 2, 1, 1, 3, 2, then the scale is determined by that. So if you know what the starting position is, and you know what all the successive differences to the various next steps are, well, then you can just recover the scale one at a time by starting here and just adding consecutively these various differences. Now, as a little aside, I have a course called the Algebraic Calculus, okay, and many of you will have watched some of the videos of that, and perhaps some of you are actually engaged in that course. It's a huge amount of work, but all kinds of interesting things are going on there. In the Algebraic Calculus, I'm really interested in bringing together the discrete side of calculus and the continuous side. So one of the things that I stress, which you usually don't find in calculus courses, is the discrete calculus, where instead of looking at derivatives, we look at differences, etc. Instead of looking at integrals, we look at summation operators. And this will be very familiar, okay, because this is what happens in the discrete calculus. You have some sequence, and you're looking at a difference operator, which just takes successive differences. And being able to recover the original sequence from the differences is possible if you know, say, the first element. So it's really exactly the same kind of story, just a small aside. Okay, so scales of the same type then, this concept we've just introduced, are obtained by rotating the tonic and keeping the interval sequence, right? Because we've said that the two scales are of the same type if their interval sequences are the same. So that means the only place where they can be different is in the tonic, or the starting note, which is sort of obvious. So for example, if we consider a new scale, t prime, say, and we know that the tonic of t prime is 4 instead of 7, and we know that the interval sequence of t prime is the same as the interval sequence of this one, namely 3, 2, 1, 1, 3, 2, then we can recover t prime. Let's do it, okay? So it has to start with 4, and this is the interval sequence. So the next one differs from 4 by 3, so it's going to be 7. The next one we have to add 2, we get 9. The next one we have to add 1, we get 10. The next one we have to add 1, we get 11. The next one we have to add 3. Okay, so this is a little bit tricky. If you have 11 and you add 3, well, it's really the same as like if it's 11 o'clock now and what's going to be 3 hours from now. You go past the 12 and you get to the 2. Okay? Or another way of thinking about it is 11 plus 3 is 14, and 14 is the same as 2 on the clock because 12 is effectively 0. So we're getting to 2. Okay, we've just added 3 to 11. And finally, we add 2 more to 2 to get 4. So this is the scale t prime, which is of the same type as this scale. So since this was a blues scale, this will also be a blues scale. Okay, and if this was started, say, on note G, which is the 7th note of the C scale, well, then this will be the blues scale starting on the 4th note of the C scale, 4th note chromatically, 1, 2, 3, 4, that's the E, so it'll be an E blues scale. And now I'm in the happy position to tell you what the modes of a scale are in a very general fashion, which goes far beyond the usual story with the major scales and the Dorian and Ionian, etc., etc. So if we have an arbitrary scale, okay, and we're sort of thinking about it as comprising a tonic and an interval sequence. So we're thinking about the scale as being encoded by that information. We've just seen that if we keep the interval sequence and we change the tonic, well, then we're going to get another scale of the same type. It's like a related scale, okay, but it's different, but it's a related scale. Now there's another possibility, which is to keep the tonic and do something, well, perhaps rotate the interval sequence. You see, from a mathematician's point of view, this is the kind of thing that one does, even if one wasn't particularly musical. You just think about, well, what can we do in this situation? You've just modified this definition of a scale in one fashion. Well, there's a symmetrical opposite or alternative way of doing things. What happens if we do that? Okay, it's a natural thing. The mathematician wants to see the entire landscape, not just in one direction. So this is a very natural thing to do, to say, okay, let me illustrate with this this sequence here again, our blue scale, 7, 10, 0, 1, 2, 5, 7. That's the scale T. Okay, the tonic is 7. The interval sequence we've seen is 3, 2, 1, 1, 3, 2. Okay, so now we can create what's called a mode, okay, of T. How? Well, we leave the tonic where it is. Okay, we're creating a new scale. Okay, it's a new scale. But the tonic, or the starting note, is going to be the same as it is for T. However, we're going to change the interval sequence for it. How? We're going to rotate it. We're going to rotate it in the following way. So, well, there's a number of ways of rotating it, but the simplest way is the same thing that happens in a bicycle race. If you have like a bunch of guys and they're all lined up, and there's a guy in the front and he's getting the brunt of the wind. The other guys are huddled behind him, and so they're racing along, okay? Eventually he gets tired and he moves to the side and falls to the back of this little line. And the guy who's in second place moves up to take the role of leading. Okay? So this way they're collectively more efficient because they rotate the job of being in the front. So that's exactly what's going to happen here. We're going to take this leading guy, 3, and we're going to let him drop off and go to the back. So this 3 is now at the back. And everybody else just sort of moves up. So 2, 1, 1, 3, 2, they move up to the front. So now we have this new sequence 2, 1, 1, 3, 2. That's a cyclic rotation, if you like, of our interval sequence. So we're now in possession of a new scale with the same tonic, but now a different interval sequence, although the interval sequence is closely related to the one that we started with. Okay, so let's write down the scale for T tilde. Well, it starts at 7, okay? And here are the various differences. So 7 plus 2 is 9. Then we add 1, that's 10. Then we add 1, that's 11. Then we add 3. Okay, we've done that before, right? 11 plus 3 is 2, we said. Okay, and then we have to add 2, that's 4. And then we have to add 3, and that's 7. Okay, we just check. Yes, is that the same as what we started at the beginning? Yes, that's good. So we've probably done it correctly. So now this is a new scale. Okay, and if you actually played it, you would sense that it actually sounds different from the original. And not just a translation that it's like up or something. It's a stronger kind of difference than just translating, at least to our ears. But it's still, in some sense, quite related to the original scale T. It's a mode of T. And you could see that you could create other modes because you could just iterate this, right? You could let rider number 2 go to the back and everybody moves forward. And in fact, how many modes are there going to be? Well, there are going to be exactly as many modes as there are entries here because every one of the riders can take their turn up at front. Okay, so there's going to be 6 modes of this scale. And one of the modes is the original scale, but otherwise there's a total of 6 modes of this scale. And this way of thinking about modes is very general because it doesn't focus on Ionian and Lydian and Aeolian, etc. Those things are quite oriented towards a major scale. Here we have a much broader perspective, lots of additional opportunities. And in my next video, I'm going to show you we can write down all kinds of interesting patterns and find lots of modes of lots of scales using this basic mathematical framework. I'm Norman Wahlberger. Thanks for listening.